Okay, so welcome to our talk. So we are talking about the Kolakoski sequence, and the Kolakoski sequence is an integer sequence, and so we can look what the ich bin hier noch nicht. Okay, so we can have a look at the online encyclopedia of integer sequences by Neil Sloan, and it has actually a quite low number in there. It's the A0000002, and it's described like this. AN is the length of the nth run in the sequence. The first number is 1, and the sequence only consists of 1 and 2. And so we can have a first look what it looks like and see what this means. So we can see the first number is 1. That's nice. It also only consists of 1s and 2s, and this is just the first, I think, 25 elements of the sequence. It will continue to infinity. And so what does this mean? AN is the length of the nth run. That means we look at the consecutive elements, how many are the equal numbers, and put them in little boxes. So we have just 1, 1, then there's 2 2s, 2 1s, and so these boxes are the runs of the sequence. And now we can have a look why this already defines the whole sequence. And so the first step is the first element is 1. And it also describes the length of the first run. So it has a box where just one number fits in. And this immediately tells us when we want to write the second number, it has to be 2, because otherwise the run would be longer. And again, we can see the second number describes the length of the second run. So we have a box where the second number fits in. And then the second number again is a 2, because it has to be the same number. And the third number again describes the third run and continues like this. So since the run is already completed, we have to write as the next number 1, because it would be otherwise the third 2. And this one again tells us the length of the fourth run. And the other number is again 1 and tells us the length of the fifth one, and basically continues like this. So we can now fill in the next numbers. And one observation is that each time, so each of these numbers makes a prediction about a run which comes later. And each time we write the 2, the prediction gets a little bit longer. And so we can see that when we again write a 1, it stays the same distance, and then it grows again, and so on. And at some point, you can say it's enough predicted and just fill in the rest alternatingly by 1s and 2s. And again, these would again predict here the next runs which don't fit on the slide. And one observation now on this sequence is that we can see that each number has a predecessor and a successor. And it also connects to one number where it's predicted by. And if it's 1, it predicts one other number. If it's 2, the prediction splits into 2 numbers which are connected to this number as well. So each number has 4 or 5 connected numbers in the sequence by this, by the linear succession in the sequence, and by the prediction about runs which come later. Somehow special are these first ones. So the 1 just predicts itself, and the first 2 predict itself and the next 2. So these are somehow special, but all the others predict something in the future. And if we now look at this sequence and just keep the boxes and drop out all the numbers, we can look how long these boxes are. So now they are again colored by boxes which are just have just place for 1 number, which are now yellow, and the boxes with 2 numbers in are blue. And if we just take these colors again to write the length of the runs, then it reproduces the same sequence. So this is where the sequence is somehow, fractal and self-describing in some way. So we could again now look at the runs of this and say it's a run of one number, of two numbers, and of two numbers and one number, and it would again go back to this. So I could repeatedly just compress the sequence onto itself. And now there are one idea to visualize this sequence is to put it in a spiral. And after we did it, we found out other people had this idea as well. So there's already images on the internet, like this one from the Wikimedia, where we can see that the numbers are now placed on a spiral. So the one is somehow ignored here because it refers to itself. But then it goes 2 and 2 and 1 and 1 and so on. And now we can see that on this spiral, we can see the predicted numbers somehow in a radial direction. And the twos always split into two predicted numbers, and the ones go radial out. And we would like to have the spiral slightly different, such that the numbers are more equally distributed along the spiral. And yeah, and that's the point where I hand over to you. It's ceremonial microphone.
So, as Uli already told us, every single one is predicted by one number and also refers to an upcoming one. The same holds true for the twos. So we come from one number and we move on to two other numbers that are somehow predicted by that very two. And this gives us a local impression of the shape that we would like to create, in sense of looking at the spiral, looking at the representation, gives us closely by the next connected numbers in our sequence. Another question is there a suitable way to go to do that? We have seen a first try done by some other mind. I'm not going to judge that anyway. And so we started with considering spirals in general. What we see here on the very second line is the general representation of an Archimedean spiral. So we have two degrees of freedom in some sense, which means here we have some freedom to choose on one hand this radius telling a function a of t, and on the other hand we have the angle velocity predicting function b of t. Another question is there a suitable choice for a of t and b of t to fulfill some of the properties we would like to have our representation in the very end? So the possibly most basic approach is to take a and b equals to t, which gives us a nice spiral, but it comes with some issues. On one hand, we see shown here by these little outgoing parts that show where our taken out image ends, in some sense that this is filling the whole plane. So not really helpful if we are aiming for visualizing the whole sequence. On the other hand, distributing the points. So these blue dots that we see here are the evaluations of b of t, so t in the natural numbers. So what we first seen in the very definition of our sequence. And we see here, okay, they are distributed somehow nicely, but yeah, we miss somehow this connection between the number and the connected following ones. So now, do we find some better choice for A and B? And yeah, there is. It looks possibly at the very first moment a bit randomly chosen, but there's a conjecture that hasn't been proven yet about that Kolakoski sequence, and that is saying which ratio is there between the number of ones and the number of twos. There has been done some improvement that so the conjecture states the number of ones and the ratio of the number of twos is 1/2. This hasn't been proven yet. There was some attempt made in the beginning of the 90s by some Czech and Canadian mathematician. My knowledge of that language is so low. Mathart, and he proved that it's nearly 1/2, so it's 1.50084, so nearly 1/2.
What is meant by 10 to 1/2?
It is the conjecture. It hasn't been proven. There is some, so he's a computer scientist. There is some proof that's showing, okay, we have something that is very close to 1/2, but it's not proven that it's really 1/2. And going back to the idea that a 1 is connected to 2 elements of the sequence and a 2 somehow to 3, and having that conjecture in mind, if we run once around, so we have the angle of 2 pi once completed and compare the numbers of points that are on each of these runs on the spiral somehow, we see that the number of points from one run to the next one grows with 1.5. So this somehow gives rise to this choice of 3/2 here. And this gives actually a nicer distribution of the points, but we still aren't able to visualize the whole sequence on one single image. And this is the next point we would like to work on, is not choosing these two equally, but find some better representation for A of t. And this was actually done by experience, so try and error. And we went with this very common approach of by saying, okay, we divide t by t plus some positive constant, so that in the limit we have a radius of 1 in the very end. Now this actually restricts the whole spiral into a unit circle and gives us the possibility on one hand to represent the whole sequence, and on the other hand to fulfill that we have these nice connections between the foretold and predicted elements on our sequence. And I think it's again time to give it back to you.
Yeah. So one thing that we can see when we look at these spirals is that that really when I look at one winding to the next, then here 2 numbers go, or 2 intervals go somehow to 3 intervals, and this repeats over and over again. So that's there we can even see that this factor of 1/2 for one to the next winding somehow works out. And then and then in the end, so this choice of 60 was just done by experimenting. So if we take a lower number, then the numbers at the center are very much spread out. Even if we would take t plus 1, then the first number would somehow here, and the center is really empty. And this number becomes too big, then very many numbers go to the center, and we don't see what's going on there. So the 60 is somehow just a trade-off between empty and cramped center of the image. And then in the end, it's just the image we created. This is now as acryl on plywood. And we can again see here the sequence going around the dark spiral. And each time one of these branches goes through the spiral, that's where a number should be. And so in this case here, it would split into 2 branches, and that's a 2. And this would be a 1 because it doesn't split. So this somehow represents now the Kolakoski sequence. To be exact, we left out the 1 in the beginning. So there's, if you just take the rules to that the sequence only consists of 1s and 2s, and it creates its own runs, then there are 2 choices you could do. And the only difference is whether there's a 1 in the beginning or not, because the 1 predicts itself. And anyway, the first 2 predicts itself in the next number, independent whether it's the first or the second number. And so in this case, to really paint the Kolakoski sequence, there would be a small ring at the center be missing, which represents the 1 which predicts itself. Yeah, and that's basically what we wanted to present. And it's also here in physical representation.